Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. So, what's on the menu today? So we are going to finish the parts on brush up that we started last week, and we are going to continue on cloud storage, aka data lakes. Before we start, as I will often do, I will ask you a few questions, and then we'll continue with the lecture. So let me switch over to the Clicker app. It's the usual address that you already know. So this is a test question on what I have told you last time. Which one of these is not a fundamental shape of data? 4 are, and 1 is not. Is it the cube? Is it the table? Is it the tree? Is it the circle? Or is it the graph? One of these is not a fundamental shape of data. The shapes of data, it's absolutely fundamental. This is where everything starts, where when you start a new project, you have to figure out the technology you're going to use, how you're going to store your data, query your data. It all starts with the shape of the data. If you don't get that right, you're going to end up with a slow system that is not going to be very fast because you're not using the appropriate shape. And you might also not be very productive because you end up writing codes that is dealing with a shape, but actually the data is in a different one, right? So now it seems that many more people have access to the Clicker app, which is wonderful. So we have already 140 answers. And there is one shape that almost everybody agrees on. You can still change your minds, which is the circle. And indeed, it's not a fundamental shape of data. We will see it actually today and tomorrow, rings actually, but it's not a shape of data. It's a physical implementation of a system. All right, so let me close this one. A few more answers are coming in. This is the circle. The cube exists, the table exists, the tree exists, and the graphs exist. And the fifth one is text, exactly, or unstructured data. It's kind of a catch-all, like everything that's not one of the other shapes is unstructured. Then I have another one for you. I would like to just get a feeling of where we are. The TA team released last week an exercise 0, so as the name indicates, it's not a real exercise. We just want you to test the exam environment and see if it works for you. So if you haven't already done so, then please do so. But already tell me right now. So did it just work like a charm, everything from the very beginning, or not immediately, but then you did the whole thing we explained, like deleting the containers, deleting the images, deleting the volumes? Often you can do that by clicking a few buttons in the desktop app, and then you do again Docker Compose up. In 95% of the cases, it solves the problem, right? So this is the one thing to try if it doesn't work. But maybe some of you had issues, and here I would like to understand, do you have an M1 or M2 chip, or is it something different? Normally, the M1 and M2 chips, now they work better than before, because it seems that Docker addressed the problem, and also the Jupyter notebooks. But still, I would like to get a feeling, right? And maybe some of you have not tried it out yet. And some people maybe just registered for the lecture and don't know. So the exam magic box is a Docker environment that contains actually something very similar to what you'll have on the exam. Of course, on the exam, it's not a Docker, it's an actual virtual desktop, but it has all the technology you'll have, right? So RumbleDB with JSONic, PostgreSQL, Spark SQL. And so in order to get you used to it, we are going to use it a lot in this semester. All right, so if you haven't tried it out yet, please do, so that you can let us know if there are any trouble, because we want to help you. So the very good news is that most of you made it work, either on the first or second try. Some of you seem to have an issue unrelated to Apple Silicon, so please contact the TAs, and they will be happy to help you and support you. It seems we have 3 people with an issue and who have M1 and M2, so please also contact the TA. Then we'll see if it's easy to solve, or if we need to learn something more about M1 and 2. Okay, thank you very much. It looks great. Do I have another question? Yes, I have a question, something that I barely told you. Maybe I did, maybe I didn't, but I would like to see if you actually can figure it out, because this is to be something important this semester. The question is, if you start with a table, what data shape do you get if you denormalize the table, like all the way down, not even in the first normal form? What kind of data shapes are you going to get if you do this? So it's related to what I told you, like the Inception movie, a table in a table in a table, but what is that? A table in a table in a table. So do we get cubes? Do we get trees? Do we get graphs? Or do we get unstructured text? Cubes is surely what you get if you bake a cake and then cut it and share it, but maybe that's not what happens with data. What do you say? Unstructured text, trees, still a very small majority for trees. Well, in fact, these are trees. We get trees. More exactly, we get a forest in the sense that it's a collection of trees, right? So a collection of trees is a generalization of a table, right? And a table is just a very specific case where the trees are all flat and all look the same. And then you get a relational table. Don't worry if it's not clear. I would like this to become very clear during the semester as we make progress. This is something that we will see is very important. And now I will switch back to the slides and continue. So I have a few slides to finish from part 2, lessons learned. Not many, really. You can see 27 left. Then we'll start with cloud storage. But the first few slides are actually just a recap of what we saw. First, data independence. The one thing I will repeat 100 times during the semester, it is a separation between the physical layer and the logical layer, where the users just deal with instances of the data model. In that case, it's a relational table, and they just focus on the data model, and that's it. The user has absolutely no idea about what's going on with the file system and the details of how it is stored, or even how it is implemented, perhaps in C++. The users couldn't care less. They have their data model, they have their query language, and they just deal with the data, and everything is just magic. And we saw that you can then swap the physical layer without actually changing the model. Then the 5 data shapes, now you know them, and we are going to actually see them all except unstructured, which is left for information retrieval or for large language models, which are also fascinating, but we'll focus on the other 4. Then a bit in the spirit of data independence, but now separating between compute and storage, there is this idea that compute storage, that's the physical part, the way we store, and it used to be in the 70s on single machine, single CPU, single disk, and now we're switching to multiple cores, multiple machines, and so on throughout the semester. And then the model, we see it's not just a table, it can also be trees, graphs, and cubes, as we will see. And finally, a language on top that is functional and declarative, that is the alpha and omega of query languages, that they should be declarative and functional. Then I reminded you of the definitions of relational tables. They are called relational because mathematical relations. But I also told you that you can see a table as a collection of tuples, can be a set, a list, or a bag of tuples, with 3 criteria that make it a table. Relational integrity, all the tuples have exactly the same attributes, so they fit into a table. Atomic integrity means you don't have any tables in a table in a table in a table. It's all flat, right? Just atomic values. And we'll take some time to define atomic value also in this lecture. Domain integrity means that in every column you have some instantiable type, like all ints or all booleans or all dates, right? So this is what it means. If you have all 3, then you have a beautiful relational table. That's the world of SQL. And then we have NoSQL, which is when you start breaking these rules, and we will break these rules in this semester, and I'll show you what it looks like when we do, what it means for the models, what it means for the language that we are going to use, because of course SQL is going to reach its limits there. All right, and this is where we stopped. Do you remember this? Select from where? Learn this by heart. The order of the clauses, this is the most fundamental building block of SQL. It's a select from where expression. It's always in that order. Select from where, group by having, order by limit of set. It is exactly in that order. but they are optional. You don't have to have all of them. You can omit some of them. Of course, you need to think when you do it. For example, if you use limit and offset, but you don't use order by, it doesn't make a lot of sense because then you're kind of picking stuff randomly. Having without group by doesn't make any sense either. So, right, you basically need to understand what you're doing. But this is in essence a flat select from where query. All right? Who is now comfortable with this one? You're going to have plenty of exercises that actually have been released, I think today at noon, so you'll be able to play with this and discuss it in the session. Beyond just the select from where, you can do a few more complicated things with SQL. One of these is that you can do the union of two select from where expressions in order to generate a table, then take the union. Of course, it also works with the intersection and the subtraction quite well. Something else that you can do is joins. In that case, so there are several kinds of joins. The most generic one compared to natural join is the theta join. A theta join means you take two tables, you kind of take the Cartesian product, but not the whole Cartesian product. You only put the tuples together that actually match. And match is defined by a predicate combining two tuples. So given a tuple and a tuple from the left and the right, either the predicate is true or if it is false, and you only keep the joint tuples if the predicate is true for these two tuples. So this is theta joins, and you explicitly give the predicate, right? So in that case, you say you're joining persons and spaceships here and here. On, and this is your predicate. You only match the tuples if you have this equality. The person's last name must be the spaceship's captain name, right? So we join captains with their spaceships. All right. So of course, it would be too easy if that was just it. And in fact, there are all kinds of flavors of joins. This is the vanilla join, but then there are so-called outer joins, full outer join, left outer join, right outer join. Sounds scary, but actually it's not. It's all about what we do with the tuples that don't have any match. What if you have a tuple on the left that doesn't find anybody on the right to match the criteria, or the opposite? There is a tuple on the right that doesn't match any tuple on the left. Well, if you have an outer join, then you just still include these tuples in the, no, what am I doing here? You still include these tuples that are lonely in the results, but you just put nulls everywhere. Null in SQL is the absence of value in a relational table, right? So you just fill this with null. It means that this spaceship here doesn't have any captain, or at least it's not in the list right here, and this captain here doesn't have any ship. Of course, it's the medical doctor. Right? Okay, so this is a full outer join. Right outer join, left outer join means that you only do this with the nulls on one side and not the other. And finally, we have the natural join that doesn't have a predicate. Why don't we have a predicate? Just because the columns are the same. So if you do a natural join, you assume that there are columns here that have the same name, and you implicitly take the predicate with the columns that match, right? So here you have last name and last name, so you just naturally use this as a predicate. And here there is no on, there is no predicate at all, it's natural, right? Be careful, only do the natural join if you're sure that you want to join on the columns that have the same names. Otherwise, you might have a few surprises. And then, of course, you have the natural full outer join, the natural left outer join, the natural right outer join, and so on and so on. So all possible combinations, but it's the same idea. Here, it's actually a full outer join. And you can see that, again, you have tuples left and right that didn't match anything, and we just fill the nulls. Okay, for whom is that clear? Okay, so joins are very expensive, right? Technically, so if you want to shine in a party with your friends, you can tell them joins can be implemented linearly. You can think of it with a hash table. You just put everything in a hash table on one side, then you look up in O of 1 for every tuple on the right. That's O of n, right? The problem is that the constant is actually high. So just because it's linear doesn't make it sustainable. So this is why we are kind of scared of this in big data. And so we like to pre-join everything, and pre-joining is just denormalizing technically. So if we had these data sets here, and here, that would be the normal form. We like to instead store that like this in the data lake, completely denormalized. Then you don't need to worry about the join, it's already done, right? So this is denormalized. Okay, now, if I take the analogy of the Inception movie, further, it's not just tables in tables in tables in tables, it's also queries in queries in queries in queries, right? So you can actually nest select from wheres in select from wheres, right? Its limit is the sky to what you can do. So you can put a select from where in that case in lieu of a table. You replace the name of a table with a select from where. You can also do this in other clauses. An example is in the where clause. And a typical example, almost a textbook example, is you use a select from where to compute the maximum value for something in a table, then you get just one value. And then you feed it into a where with an equality. So you select the items where the value is equal to the max, and that's actually a computation of the argmax, right? So the textbook example of a nested query is the argmax computation. Yes, go ahead, the microphone on. Hello?
Yeah, okay. Can we natural join two tables with two columns having the same name?
Yes, absolutely. Then it basically matches on the two columns, if that happens. It basically matches all of the columns that are on both sides. Was it your question? Otherwise, we'll take it as a yes. Yes, awesome, perfect. Thank you for asking. Okay, and don't hesitate to have any questions, right? They are less shy on Zoom than in the room, it seems. So don't hesitate to raise your hands and interrupt me. Okay, now what are these Greek letters? So I assume you learned at least the beginning. I mean, everybody knows the beginning of the Greek alphabet, but maybe not the entire alphabet, but I'm sure you know these, right? Sigma, gamma, pi, and so on. This is how the formal people, the formal researchers on SQL, this is what they like to do. So sigma is for selections, pi is for projections, gamma is for grouping. So they have a letter for everything. Then they love to write beautiful formulas to basically do the math. Of course, I prefer SQL. Well, I also like the letters and so on, but SQL is kind of simpler to learn, but it's kind of equivalent. Now, this here is physical. SQL, what you write in SQL when you reason is the logical level. This here is a query plan. It means it's a physical suggestion of how to actually implement your select from where query, your SQL query. And in fact, what's happening behind the scenes is that the query engine that is implemented otherwise in C++ and Java might find some things in your query that are not very well written or that are a bit inefficient. And then the magic happens because the query engine is able to rearrange this and change the way that it's structured in such a way that's going to make it faster, but without changing the results. And here, this is where the math happens, mathematical equality between the query plans, equivalence. Okay, so this here is the physical plan. So if you ever see these Greek letters, then you'll know what these are. Another peculiarity of SQL, and that's just by design, it's not two-valued logic, it's three-valued logic. It means that you just don't use true and false, but you have true, false, and unknown. Some people call it null, the unknown. There's a slight difference, so it's like a null, but some people like to call it something else. So this is why they call it unknown. Anyway, it just means you don't know if it's true or false. And here again, it's common sense. Because, yes, we have a question?
I am not sure if it fits with the current topics, but since joins are so expensive, are there instances where even in the big data landscapes, companies need to do joins? And if yes, how do they do that, especially for data sets where we need multiple machines to work with each other to process the data?
That's a very good question. In fact, we'll answer it in a few weeks, but I'll still give a bit of answer now. Joins will never be completely avoidable. You can avoid, if you know in advance what you're likely to be joining, then you can denormalize in advance, but you cannot always do this, and it might still be when you have your data already in the cluster that you need to actually do a join. How a join is done is actually very similar to the idea of the hash table that I mentioned earlier that you can do on a single machine. But basically, what you do is you use something called shuffling, and we'll see shuffling a lot in this lecture, meaning that you send over all the tuples from the left and all the tuples from the right on the same machine if they match, right? That's kind of the idea. It doesn't work with all the joins. It works with some of them. We'll see which one, but there are cases where you are able to just shuffle the tuples around in such a way that those that match will be on the same machine. And then the problem comes down to a local join on each one of the machines, and then you magically get petabyte of join table, right? And again, join happens. We had a guest lecture a while ago by Databricks, where an engineer was explaining that there are cases where you still need to do joins. Okay? It's all about optimization. Whatever you can optimize, do it, but sometimes you cannot know everything in advance of what you need. Did I answer your question? Yes, wonderful. Okay, now this three values logic, it's kind of common sense, right? If I tell you anything or true, it's always going to be true. It doesn't matter if it's true or false, this anything, right? Who agrees with that? Right? Anything or true, that's going to be true. So this is why unknown or true is actually true, right? So you can figure out, do it maybe offline, but you will see that it makes sense, the way that it's filled in there. But basically, it's three values logic, right? So be careful because this is how it's done in SQL. Now, a bit of terminology, DML, DDL, who heard of that? Okay, these are just some three-letter abbreviations. Basically, in SQL and actually in query languages in general, you have two kinds of queries that you can write. There are the queries that actually manipulate the metadata. Here, data definition. So you rename a column, you add a column, you remove a column, you rename a table. This is all metadata, right? Creating a table and so on. It's called DDL, data definition language. And everything that's about querying the data with select from where, or maybe inserting, removing rows, which you can also do in SQL, even though I didn't show you, this is called data manipulation language, or DML, right? So whenever you hear DDL, DML, this is what it means. Something else that I want to throw at you, again, it sounds very short, right? Because this actually takes weeks to teach the details of that. Indices. Indices accelerate the query. This is the benefit of using a declarative and functional language like SQL, as opposed to an imperative language like C++ or Python or Java. So the idea is that when you have a select from where, and you look for a very specific person among billions of persons, if you don't have an index, it's going to take a while. You need to scan through the entire data set until you find the person. But if you have an index, it's very similar to what you have at the end of your books. Very often on the last pages of a book, there is an alphabetical list of terms together with the pages. This is an index. It's very similar to what we have in relational databases. And that actually makes the query, without any modification, still a select from where, but except of taking 2 hours, it's going to take a few milliseconds. That's the magic of using a query language that is declarative and functional. Right. And of course, the implementation itself is in an imperative language, of course, right? C++, Java, Python, and so on, but it's hidden from the user. Nobody has to actually deal with this. They can just stay on the high level, the end users. Okay? Yet another distinction is, and I think there was a discussion on the forum about this part of an answer I gave, you need to ask yourself, when you deal with data, what are you doing? Are you reading or writing to the data sets, right? If you have an inventory system in your company and you keep adding items, removing items, customers place orders, they pay, and so on, the data keeps changing. This is write intensive, right? It's also called OLTP. Then you want to use a system like PostgreSQL or a database system that handles this efficiently. If you do data analytics and you don't need to modify the data, you're just reading it, then this is called OLAP, online analytical processing. This is online transactional processing, transaction processing. So this is completely different. And in fact, the idea of denormalizing the data has to do with read-intensive scenarios, while here you want normal forms if you write a lot. That's kind of the idea.
We have another question.
Yes?
In a company I worked, we used sharded views, create view. Can a view be seen as a denormalization of multiple tables? It was a read-intensive database.
Sharded views, yes. A view can be used to denormalize. The view could be joins, a join of tables. The real actual denormalization happens if you materialize your view, because a view is basically a virtual table if you want. A view can be materialized or not materialized. Materialized means that you compute and you store a copy of the view somewhere, and then accessing it is just like a table. If you don't materialize it, then you always do it on the fly. You rebuild it on the fly whenever you want to look at the view, right? This word, materialize, will also be one of the words that will be important in this lecture. And I'll talk about materialization many times, right? So I would say there is a link between views and denormalizing, but the real denormalization really usually implies materializing the denormalized data sets, right? Did I answer a question? Yes.
Yeah, that's
Okay.
the answer.
Thank you. All right. Yes?
You said you prefer the normal when we have quite intensive operation, right?
Yes, that's basically it's a rule of thumb. Of course, it's never 100%, right? But the rule of thumb is this. The reason is if you write a lot and you do not have your data set in normal form, you're going to have trouble. And the name of this trouble is update anomaly, insert anomaly, and what's the third one? Insert anomaly, update anomaly, delete anomaly, right? These are the terrible things that will happen if you don't have normal forms and you're writing a lot, all right? Of course, there are other criteria. If you look at the Moodle forum, I gave some other criteria regarding this. Okay. Now, here is one of the probably the most fundamental features or powerful features that a database management system like PostgreSQL offers, and you don't get that out of the box of a language. It's transactions. What happens if you have thousands of people at the same time writing to the database? How do you deal with this without crashing the system? There is this acronym that is very easy to remember, ACEs, atomicity, consistency, isolation, durability. It basically means in the case of atomicity that either your whole transaction, meaning a sequence of queries, succeeds or it doesn't. Keep in mind the ATM. You want to have the banknotes in your hand if and only if your account gets subtracted, right? When the amount gets subtracted from your account. Atomicity means it's either or. Either you don't get the banknotes and nothing is deducted from your account, or you get the banknotes and it's deducted from your account. All right? Then you have consistency, which is that you must have at all times a consistent state. An example of that is referential integrity. It means that if you have a reference from a starship to a captain, the captain must exist. And in fact, in our case, that wasn't the case, right? But a database system can ensure consistency in this way, right? Another example that is now the I of ACID is isolation. Ideally, if there are 1,000 people using the system, you should feel like you're the only one, right? It's like in a shop, there are thousands of customers, but every customer must feel unique, right? So this is exactly the same thing. It feels isolated. You don't see that 1,000 other people are actually changing the system. This is called isolation. The last one is durability, which is that if you store something in your system, like the paper that took you 2 months to write and that you submit to a conference, you don't want the paper to just disappear as soon as you pull the plug, right? So this is durability. You must make sure that the updates will not disappear. And again, the database management system makes sure of this, okay? We'll see that this but I'll come back to that. At large scales, it's really not easy to do. And in fact, people try. To some extent, they succeeded, but some compromises needed to be made. So from this, how do we move on to the rest of the lecture? Well, we do in 3 ways. We might see data sets that have lots of rows, billions, trillions, quadrillions of rows. We'll see systems that have lots of columns, meaning more than 255, which is the typical limit in a system. Now we'll see thousands or millions of columns. Of course, you can imagine if we have both lots of rows and lots of columns, then it's sparse, right? You don't have a value in every cell, obviously. And finally, a lot of nesting, like this inception thing, right? Tables in tables in tables. And what is the shape we get? Trees, exactly. Wonderful. So this is it. This is the menu for the rest of the semester. We'll deal with lots of rows, lots of columns, lots of nesting. And data independence, materialization, denormalization, so all of these concepts. All right, any questions? Then I move on to cloud storage in the lecture hall. No question on Zoom? No questions? All right, so this is the moment to temporarily say goodbye. I'll stop the recording, then I'll start it all over again on the cloud storage sites.